we have to transfer this accurately measured 4.85 grams of potassium chromate quantitatively via this funnel placed into this neck of the measuring flask, which is 250 cubic centimeters.
Then we rinse the potassium chromate crystals down from the weighing beaker. Every crystal must be rinsed, and you must make sure nothing remains behind.
We then have to rinse down all the crystals. Once the flask is filled halfway, we can remove the funnel and place the stopper in, and then we have to shake it until everything is dissolved.
Then we place the measuring flask on a horizontal surface, remove the stopper, and use the wash bottle to add water until the bottom of the meniscus is exactly in line with the mark on the neck of the flask.
Now you must refer to reference number 304.3 in your workbook for further calculations on concentrations of solutions. Stop your videotape now to attend to worksheet 304. This brings us to organic chemistry, which is a study of the compounds of carbon. We can't even imagine to think how modern society could exist without carbon compounds. You know, carbon compounds are found in textiles, foodstuffs, insecticides, medicines, antibiotics, vitamins, all these compounds like plastics, etc., etc. Fortunately, the vast number of organic compounds can be classified in so-called homologous series. Now, what is an homologous series? An homologous series is a family of compounds that exhibits similar chemical properties due to the same functional group in the compound. Furthermore, an homologous series can be represented by a general formula. The unique multiplicity of carbon compounds is due to the ability of carbon atoms to combine with other carbon atoms to form straight chains, branch chains, and ring compounds or cyclic compounds. Now, the simplest type of organic compounds are the so-called hydrocarbons, which only consist of hydrogen and carbon atoms. And the simplest type of hydrocarbons are the most basic compounds in organic chemistry, which are the alkanes. Now, the alkanes form an homologous series of saturated hydrocarbons. What does that mean, saturated? It means the compounds only contain single carbon-carbon bonds. And the general formula is CnH2n plus 2, where N is the number of carbon atoms in a compound. Now, let us look at the first four members of the alkanes. When N is 1, we have our first member, methane, where meth is the numeral prefix used for any organic compound containing only one carbon atom. The formula is CH4, semi-structural formula, still CH4. And this is our structural formula where we see the carbon is surrounded by 4 lines, each representing 1 covalent bond. You see, carbon belongs to group 4, so it has 4 unpaired electrons, and therefore it can form 4 covalent bonds as we see here. Now, the second member with N equals 2 is ethane. Now, eth is the numeral prefix for any organic compound containing 2 carbon atoms. Our formula is C2H6. N is 2 in this case, so we have H is 2N plus 2, which is 2 times 2 is 4 plus 2 is 6. This is our semi-structural formula. In the semi-structural formula, we group the hydrogen atoms which are attached to a particular carbon atom together like this. And here again we see the structural formula or the spatial arrangement with all the covalent bonds shown. Our third member with N equals 3 is propane, where prop is the numeral prefix for any organic compound containing 3 carbon atoms. What will our formula look like? We have 3 carbon atoms, N is 3. H2N plus 2 means 2 times 3 is 6 plus 2 is 8. This is our semi-structural formula, CH3, CH2, CH3, and our structural formula with all the bonds shown. Our fourth member with N equals 4 is butane. But is the numeral prefix for 4 carbon atoms. What is the formula now? C4, N is 4 now. H2N plus 2, 2 times 4 is 8 plus 2 is 10. In the case of butane, we can have 2 structural isomers. Now, what are structural isomers? They are compounds with the same formula. In other words, they have the same number of atoms of each element, like 4 carbons and 10 hydrogens in this case. But they have different structures, and therefore they have different physical and chemical properties. The first structural isomer for butane is normal butane, where we have all the carbons in one straight line, like this. A straight chain, we call it, normal butane. But we can also have this compound, where we also have 10 hydrogen atoms, 3 and 3 is 6 and 3 is 9 plus 1 is 10. And we also have 4 carbon atoms, but they are arranged differently in space. Now, when we name organic compounds, we always number the longest carbon chain starting from the end nearest the carbon atom where we have the branch or the substituent. We have substituted a methyl group in this case. Now, what is a methyl group? It's also called a methyl radical, where 1 hydrogen atom from methane is removed, and then we get the methyl group. Now, this methyl group was substituted on carbon atom number 2. So, when we name the compound, we first write the number of the carbon atom on which we did the substitution. So, it's 2. What did we substitute on carbon atom 2? A methyl group. And we have prop here, which indicates the longest chain consists only of 3 carbon atoms, and the name ends in ane, indicating that we only have single carbon-carbon bonds because the compound is saturated. Let us see how we can name a more complex alkane like this. Now, the first step is to identify the longest carbon chain. In this case, we have 1, 2, 3, 4, 5, 6 carbon atoms, so this is a substituted hexane. We start numbering our carbon atoms in this longest chain, starting from the carbon closest to the substituents. So this is carbon 1, 2, 3, 4, 5, and 6. And we substituted methyl groups on carbon atoms 2, 3, and 5. So the proper name of this compound is 2, 3, 5, trimethyl, because we have 3 methyl groups, hexane, because there are 6 carbon atoms in the longest chain. It would be wrong to number the carbon atoms from left to right, because that will give us a name of 2, 4, 5 trimethyl hexane. So this name would be wrong. Why? Because we would not then have given the numbers of the carbon atoms the lowest possible values as on the longest carbon chain. Now, let us look at the reactions of the alkanes. First of all, let us look at combustion. The alkanes like methane, ethane, butane, octane, etc. will all react with oxygen in air to give the same combustion products, carbon dioxide and water vapor every time. And we also find that the heat of reaction is always negative for all these reactions. And the potential energy curve also indicates that we have an exothermic reaction because heat is always evolved. So for this reason, the alkanes are extensively used as fuels. Alkanes also undergo substitution reactions where 1 or more hydrogen atoms are substituted by other monovalent elements, like the halogens, to produce the so-called haloalkanes or alkyl halides. Now, the formula is simply written as Rx, where R stands for the alkyl radical, formula CnH2n plus 1. In other words, the same formula as for the alkane, with one hydrogen atom removed. And the X represents the halogen, fluorine, chlorine, bromine, or iodine. Now R, which is CnH2n plus 1, is the alkyl radical. Let's see how these alkyl radicals are formed. When one hydrogen atom from methane is removed, we get the methyl radical CH3 with this structural formula. When one hydrogen atom is removed from ethane, we get the ethyl radical CH3CH2 with this structural formula over here. And when one hydrogen atom is removed from propane, we get the propyl radical CH3CH2CH2 with that structural formula over here. Let us look at some substitution reactions of alkanes. In the presence of sunlight or UV light, you will find that the halogens like fluorine, chlorine, bromine, or iodine will displace one hydrogen atom from an alkane like methane to produce, in this case, chloromethane, because we use chlorine. And this is the structural formula for chloromethane, and also HCl is formed. When we use ethane and we react with chlorine as the halogen, in the presence of sunlight or UV light, we get chloroethane, where one hydrogen atom is displaced by a chlorine atom. This is the structural formula for chloroethane, and this is HCl also formed. Let us look at a few more examples of haloalkanes. When one hydrogen atom from methane is substituted, we get chloromethane. This is our semi-structural formula. And here we have the structural formula with only one chlorine atom attached to the methyl group. When we substitute two hydrogen atoms from methane, we get dichloromethane. Can you see the formula now is CH2Cl2? And this is our structural formula. Can you see there are two chlorine atoms attached to the carbon in this case? When three hydrogen atoms are displaced by chlorine, we get trichloromethane, commonly known as chloroform, CHCl3, with this structural formula where we have three chlorine atoms attached covalently to the carbon atom. When four hydrogen atoms are all displaced by chlorine, we get tetrachloromethane, also known as carbon tetrachloride, CCl4, where the central carbon atom is attached to four chlorine atoms by covalent bonds. The second example of hydrocarbons is the alkenes, which form an homologous series of unsaturated hydrocarbons. What does that mean? It means each compound contains at least one carbon-carbon double bond, or we have two covalent bonds between the same carbon atoms. And the general formula is CnH2n, so we have twice as many hydrogen atoms as carbon atoms. Let's look at the first three members of the alkenes. Our first member with n equals 2 is ethene. The eth, the numeral prefix, indicates that we have two carbon atoms in the molecule. This is our formula C2H4 because we have twice as many hydrogen atoms as carbon atoms. This is our semi-structural formula, CH2CH2. And here we have the structural formula indicating at least one carbon-carbon double bond, which is our functional group. Our second member with three carbon atoms is propene. Prop is the numeral prefix for three carbons. We have three carbons. We have twice as many hydrogen atoms. And this is our semi-structural formula. And here we have the structural formula where we see that each carbon is always surrounded by four lines because the valency is always 4 in our structural formulae. Now the third member is butene, the but indicating that we have 4 carbon atoms. And we have twice as many hydrogen atoms, so we have 8 hydrogen atoms there. In this case, we can have 3 structural isomers. Now, we look at the first example here. When we name alkenes, we always first locate the longest carbon chain containing the double bonded carbon atom, or the alkene functional group. So we start then numbering our longest chain from this end, the end nearest the double bond. So this will be carbon atom 2, 3, and 4. And this will then be but 1-ene, because the double bond follows immediately after carbon atom 1. But the double bond can also be situated after carbon atom number 2. So in this case, we can number the compound from either end 1, 2, 3, and 4. That's the longest carbon chain containing the double bond. And the name of this compound will be but2-ene, indicating that the double bond follows immediately after carbon atom number 2. But we can also have a substituted compound here, which also contains 8 hydrogen atoms and 4 carbon atoms. In this case, we see that the longest carbon chain containing the double bond only has 3 carbon atoms in it. So this is a substituted propene. We number the longest chain nearest the double bond. So this is carbon atom 1 and 2 and 3. And we have a methyl group substituted on carbon atom 2. So the name will be as follows. It will be 2 for the number of the carbon atom on which substitution takes place. Then methyl, which indicates the group substituted on that carbon atom. Prop, indicating that we have 3 carbon atoms in the main chain containing the functional group. 1 indicating that the double bond follows after the first carbon atom. And ene, indicating that the compound contains a double bond, so we have an unsaturated compound. Alkenes undergo addition reactions when one of the bonds of the double bond is broken and one monovalent element is added to each of the doubly bonded carbon atoms, causing the compound to be saturated, because now we'll only have single carbon-carbon bonds. Let's look at the addition reactions of alkenes. When I add hydrogen gas to ethene, I get 1 hydrogen atom attached to each of the carbon atoms. And now we'll have the saturated hydrocarbon ethane form, because we now only have single carbon-carbon bonds. When I add a halogen like chlorine to ethene, 1 chlorine atom is attached to the 1 carbon and 1 is added to the other carbon atom. And we get this compound with the 1 chlorine attached to the 1 carbon and the other to the other carbon. The name will be 1,2-dichloro, because we have 2 chlorine atoms. Ethane, because there are 2 carbon atoms in the long chain. And the name ends in ane because the compound is now saturated. Now this reaction is the basis for the testing for saturation or unsaturation of hydrocarbons. When we take the compound cyclohexene, which contains 1 double carbon-carbon bond or unsaturated carbon-carbon double bond, and we add molecular bromine to it, which is reddish brown, then 1 bromine atom is added to each of the doubly bonded carbon atoms, and we get this saturated compound, which is called 1,2-dibromocyclohexane. Now, in this test tube here, I have what we call bromine water, because we have bromine dissolved, molecular bromine, dissolved in water. Let's see what happens if I add this cyclohexene to it. I'm going to shake the solution. And can you see the color disappears? Because the bromine is being added to the double bond. The bromine is being used up. That's why it goes colorless. But what happens if we add cyclohexane, which is a saturated compound, to bromine water in this test tube? Let's see what happens. Let's shake the mixture. Can you see in this case the color will not disappear because the bromine is not used up, because we haven't got any double bonds where the bromine can be added. Now, if we take HCl gas and we add it to ethene, then the hydrogen atom will be added to the 1 carbon atom and a chlorine atom added to the other carbon atom to give this saturated haloalkane that we call chloroethane. If we add water to ethene, then the OH part of the water is attached to the 1 carbon and the H atom to the other carbon, and we get an alkyl that we call ethanol. The last examples of hydrocarbons are the so-called alkynes, which form an homologous series of unsaturated hydrocarbons. Why unsaturated? Because we have a triple bond between the same carbon atoms, or 3 covalent bonds between the same 2 carbon atoms. The general formula in this case is CnH2n minus 2, where n indicates the number of carbon atoms. Let's look at the first 3 members of the alkynes. The first member has n equal 2, which is ethyne. Eth is the numeral prefix for 2 carbon atoms. And we have 2 hydrogen atoms. This is the semi-structural formula with a triple bond between the carbon atoms. And here we have the structural formula. We can again see that each carbon is surrounded by 4 covalent bonds as usual. Our second member, in this member we have 3 carbon atoms. So this is propyne, where prop is the numeral prefix for 3 carbon atoms. And we have H2n minus 2, which means 2 times 3 is 6 minus 2 is 4. So we have 4 hydrogen atoms. Here we have the semi-structural formula, and here we have the structural formula. Now, to name alkynes, we again locate the longest carbon chain containing the functional group, the triple bond between the carbon atoms. And then we start numbering the carbons from the end nearest the triple bond. So this is 1, 2, 3. And this is therefore called prop, because there are 3 carbons in the main chain. 1, because the triple bond follows after the first carbon atom. Ein, to indicate that we have a triple bond between the carbons. The third member has 4 carbon atoms in it, so it's butene, but referring to 4 carbons. And the formula is C4H6, because we have H2n minus 2. 2 times 4 is 8 minus 2 is 6. In this case, we can have 2 structural isomers. In the first case, we have the triple bond following the first carbon atom. And again, we number the carbon atoms in the longest carbon chain, starting from the end nearest the functional group, or the triple bond. So this is carbon atom 1, 2, 3, and 4. And this will be called but1-ine, because the triple bond follows after the first carbon atom. But we can also have the triple bond following the second carbon atom. So we start numbering from the left, carbon atom 1, 2, 3, 4. And this is called but2-ine, because the triple bond follows after carbon 2. And the ending of the name ine indicates that this is an unsaturated alkyne. Just like the alkynes also undergo combustion reactions, and the combustion products are the same: carbon dioxide gas and water vapor. And a lot of heat is released in this case because the reactions are exothermic. They can even cut metals by the oxyacetylene flame. But alkynes also undergo addition reactions at the triple bond. Let us look at some examples of addition reactions of alkynes. When we add hydrogen gas to ethine, which is unsaturated, 1 hydrogen atom is added to each of the triply bonded carbon atoms to give us this compound, which is ethene, which is still unsaturated. We can add a second molecule of hydrogen gas to give us the saturated compound ethane, because we now only have single carbon-carbon bonds. If we add a halogen like chlorine to ethine, which is unsaturated, 1 chlorine atom is added to each of the triply bonded carbon atoms. And now we get 1 carbon taking a chlorine atom and the second carbon atom with another chlorine. So this is called 1,2 dichloro, because of the 2 chlorine atoms. Ethene, because you see, we still have a double bond in the compound, and the compound is still unsaturated. We can therefore add a second chlorine molecule, and 1 chlorine is added to each of the doubly bonded carbon atoms to give us this compound here, where we number the carbons 1 and 2. Carbon atom 1 has 2 chlorine atoms attached to it, and so has carbon atom 2. So this is then called 1, 1, 2, 2 tetrachloro, because there are 4 chlorine atoms. Ethane. This compound is now saturated because we only have a single carbon-carbon bond in the compound. When we add HCl to ethine, then the H atom is added to the 1 carbon atom and the chlorine atom to the other triply bonded carbon atom. And we have this compound that we call chloroethene. You see the chlorine goes on the 1 carbon atom and the H atom onto the other. Now this is still unsaturated. We can add a next molecule HCl, where the 1 atom goes onto the 1 carbon atom and the chlorine onto the other doubly bonded carbon atom. And this gives us the compound where we have 1 chlorine on carbon 1, 1 chlorine on carbon 2. So this is 1,2 dichloroethane, which is now saturated. This last product is the minor product, because according to Markovnikov's rule, the chlorine part of HCl would rather be added to the carbon atom with the least hydrogen atoms. So it will be added to carbon atom 1, where the other chlorine atom is already present. We number the carbons 1, 2 from the end closest to the substituents, and now the name will be 1,1 dichloroethane, and the compound will be saturated.
At this point, we need to look at elimination reactions. Elimination reactions are the opposite of addition.
During elimination reactions, two atoms are removed from two adjacent carbon atoms of a saturated molecule to form an unsaturated alkene.
Addition polymers, including the plastics, are some of the most important products formed when small units, called monomers, are added repeatedly to form giant macromolecules.
Addition polymerization follows a so-called radical mechanism in 3 steps: chain initiation, chain propagation or progression, and chain termination.
The polymer chain is usually initiated by a highly reactive free radical, obtained by homolytic cleavage of the covalent bond or shared electron pair of an organic peroxide to form 2 free radicals.
Chain initiation continues when this free radical bonds with ethene to form a new free radical. One of the covalent bonds in ethene is broken when one electron of the shared pair joins with the unpaired electron of the free radical to form a shared pair or a new covalent bond, while the other electron of the shared pair moves to the terminal carbon atom to form the new free radical.
Chain progression takes place when this new free radical is joined covalently to a second ethane molecule to produce a chain-extended new free radical. This process of adding ethane monomer molecules is repeated hundreds of thousands of times in a short time period until we get chain termination.
Chain termination. The chains can be terminated by 2 free radicals joining up by sharing their unpaired electrons to form a covalent bond, or when a free radical chain joins with this free radical.
Let us summarize the process whereby the N molecules of ethene undergo polymerization to form polyethene, also called polythene. The bottom diagram shows the structure of a small section of the chain.
A variety of addition polymers is produced in industry by making use of different substituted ethenes as monomer units.
When one hydrogen atom of ethene is substituted by a methyl group, the monomer of propene is obtained. Polypropylene is produced. A small section of the chain of polypropylene is shown.
When the hydrogen atom on ethene is replaced with the chlorine atom, the chloroethene or vinyl chloride monomer is formed, which polymerizes to form polyvinyl chloride. The small section of the chain is shown.
When one hydrogen atom of ethene is substituted by the phenyl group, the monomer phenylethene or styrene is obtained, which polymerizes to form polystyrene. A small section of the chain is shown.
We noted that the reactivity and the classification of organic compounds are based on active centers in the molecules that we call functional groups. Now, what is a functional group? A functional group is an atom or a group of atoms causing the compound to exhibit certain characteristic properties. Let me give you some examples of very important functional groups. Now, firstly, we have the functional group where we only have single carbon-carbon bonds. The group name in this case will be alkanes. Let's take the example ethane, where we have 2 carbon atoms and a single bond between them. The suffix in this case is ane. The name ends in ane. When we have the alkenes, we will have a double bond between the carbon atoms, like ethene, and we have there the double bond, can you see? The name ending in ene. Now, the alkynes have a triple bond between the carbon atoms. That is our functional group. Let's take the example of ethyne, where we have 2 carbon atoms with a triple bond in between, and now the name will end in -ine. When we have a halogen X, like fluorine, chlorine, bromine, or iodine attached to an alkyl radical, in other words, to a carbon atom, we get the haloalkanes. For example, chloroethane, where one of the hydrogen atoms from ethane is substituted by a chlorine atom. And again, the name now ends in -ane. When we have the alcoholic functional group, OH, attached to an alkyl radical, we get the alkanols or alcohols, like ethanol, eth indicating 2 carbon atoms, where one of the hydrogen atoms of ethane is substituted by the alcoholic functional group OH. And now the name will end in -al. When we have 2 alkyl radicals like R and R accent, which could be different alkyl radicals, on both sides of an oxygen atom, then we have the ethers, like diethyl ether, or simply known as ether. Can you see we have an ethyl group on this side of the oxygen atom and another ethyl group on the other side of the oxygen atom? We can have the ketones, where we have an alkyl radical or 2 different alkyl radicals on either side of the so-called carbonyl functional group, C double bond O. Let's take the example dimethyl ketone, commonly known as acetone, nail polish remover. Here we have a methyl group and another methyl group on either side of the carbonyl functional group. Then we have the aldehydes, where we have a carbon double bond O, carbon single bond H, which is our functional group. And here we have the example ethanol, or commonly known as acetaldehyde, where we have the methyl group attached to our functional group. In this case, the name will end in -al. Then we have the very important carboxylic acids, and this is our functional group for carboxylic acids, a carbon double bond oxygen, carbon single bond O, and then single bond H. The example we take here is ethanoic acid, or acetic acid, commonly known as. We have 2 carbon atoms in this compound, can you see? And that's why it's ethanoic acid. Now the name ends in noic acid. And finally, if the hydrogen atom from the carboxylic acid functional group is displaced by an alkyl radical, we get the esters, like ethyl ethanoate, commonly known as ethyl acetate. Can you see here we have an ethyl radical displacing the hydrogen atom in ethanoic acid. And now the name ends in -ate. Let's have a closer look at the homologous series of alcohols, also called the alkanols. This is our general formula, CnH2n plus 1OH, where this is our alkyl radical R, and this is the functional group, the OH alkanol functional group. Putting those 2 together, we get ROH for an alcohol. Let us look at the first 4 members of the alkanols. With n equals 1, we have methanol, CH3OH, and this is our structural formula. Can you see carbon has 4 covalent bonds to it? Our second member is ethanol. The eth means 2 carbons, and this is like ethane with 1 hydrogen replaced by an OH group. And this is our structural formula for ethanol. Our third member, propanol, has 2 structural isomers. In the first case, we have this one where the functional group is attached to carbon atom number 1. Now, when we name the alkanols, we always find the longest carbon chain containing the OH group, the alcoholic functional group, and then we number the carbon atoms from that end, 1, 2, 3. So the name in this case is propan because there are 3 carbons in the longest chain, 1 because the OH group is situated on carbon atom 1, all because it's an alcohol. Or we can have this structure here where the functional group, the OH group, is situated on the second carbon atom. We number the longest carbon chain, 1, 2, 3. And now the name will be propan because there are 3 carbon atoms in the longest chain, 2 because the OH group is situated on carbon 2, and all because it's an alcohol. Our fourth member is butanol. In this case, we can have 3 structural isomers. In the first isomer, we have the functional group on carbon atom 1, and we number from that end, 1, 2, 3, 4. And this is now butane because there are 4 carbon in the main chain. And we have 1 all because the OH group is situated on carbon atom number 1. Or we can have the OH group situated on carbon atom number 2, which gives us butane 2-ol. Or we can have this substituted branched chain compound where the main chain contains 3 carbon atoms, and we have a methyl group on carbon atom number 2, as well as the functional group for the alcohols OH on the same carbon atom. So this will be 2-methyl propan 2-ol.